If functions were human, Asymptote would probably be their airline. Hey guys, I want to quickly talk about asymptotes of functions. Now, asymptotes are sort of like what's supposed to be a part of a function, but somehow, based on one reason or the other, they are not part of the function. And we have three of them. We have the vertical asymptotes, we have the horizontal asymptotes, and we have the oblique asymptotes. Some people also call it the slant asymptotes. So I'm going to be going into them in detail. So the first one we have is the vertical asymptote. Now, the vertical asymptote is just like a straight line. Just like I've said, asymptotes are those things that are supposed to be part of a function, but somehow they are not. Now, for vertical asymptote is a vertical line that the function is going to behave like it wants to touch it, but the function will not be able to touch it. So, and since it's a vertical line, that implies that the function would have to stretch to an extent to be able to reach that vertical line. As we can see from the background here, we can see a graph of the function in blue and the asymptote line in white. So we can see that as the function goes up, or as it goes down in this case, the function is trying to touch the white line, which is the asymptote, which is the vertical asymptote. The function will not be able to touch it. And this behavior is for functions of this nature. So if we have a function, say y equals 1 divided by x minus 2. Now what happens is that when you plot the graph of this function at x equals 2, because if you substitute x equals 2 in this function now, you will get infinity, positive infinity. So that x equals 2 can be regarded as the vertical asymptote of this function. Now let's take one last example. Now if we have something of this nature, let's say we have y equals x plus 2 divided by x squared minus 4. Now we know that this function can be rewritten as x plus 2 divided by x minus 2, then x plus 2, since we have difference of two squares there. Now we see that at the denominator here, there are two values that will make the denominator to be equal to 0, either when x equals to 2 or when equals plus or minus 2. However, we can see that this x plus 2 can cancel out. And it is when we have this x plus 2 that we have x plus 2 equals 0 implies that x equals negative 2. Now, so what we can say here is that x equals negative 2 is not going to be able to be a vertical asymptote, but x equals 2 is going to be able to be the vertical asymptote. The reason is because x plus 2 cancels out, while x minus 2 does not cancel out. So two things to take note is that the value of the function that will make the function to be equal to plus or minus infinity. That's why you have that it occurs where the function goes to plus or negative infinity. So, and that such value, just this entire equation, x equals to 2, is the vertical asymptote. Quickly, let's move to the horizontal asymptote. For the horizontal asymptote, the way they behave is such that, just like I explained in the vertical asymptote, for the horizontal one, it's like an horizontal line that the function would also not be able to get to. Now, for the vertical asymptote, we were going up, that is, the function is the one doing the behavior. But now, it is the argument of the function that will be doing the behavior, because as we can see here, the horizontal line extends to the right and extends to the left. So this is the behavior of a function when the x approaches infinity. So the behavior of a function f of x as x approaches plus or minus infinity. So this is a place when x becomes very big, the function would seem very close to that horizontal line, but the function will not be able to touch it. Such horizontal lines are known as the horizontal asymptote. And how do we determine them? It's very basic. If you have a denominator which is greater in degree than the numerator, then the horizontal asymptote will be y equal to 0. For example, if you have something of this nature, let's say you have x plus 2 divided by x squared plus 2. As you can see, the denominator has a higher degree than the denominator, so the asymptote of these horizontal asymptote will be y equals to 0. And then another thing is if they have equal ratio, for instance, if let's say you have 3x squared minus 2x plus 1a, and you have x squared, let's say this place is, let me make it like something like 4x. So let's say this is 4x plus 6. Now, the coefficients of they have the same degree 2 and degree 2. The coefficients are 3 and 4 respectively. So that implies that the asymptote, the horizontal asymptote will be y equals 3 over 4. And lastly, if the numerator's degree is bigger, then you have no horizontal asymptote. That is, if this were to be here and this would come down here, then there will be no horizontal asymptote. And that's just the basic thing about horizontal asymptote. The last one, which is very, very not common, is what we call the oblique asymptote, or sometimes people call it the slant asymptote. Now, what is that it look like? Is you have, let's say, a polynomial. Now, let's say you have a polynomial function and it occurs when the degree of the numerator is 1 more than the degree of the denominator, which implies that, let's say you have something of this nature. Let's say you have y equals x squared plus 1, and you have this y equals x squared plus 1 divided by x. So all you need to do is to do the long division of polynomial. Now, if you do the long division of polynomial, this will give you a quotient of y equals x. Y equals x. I believe we all know how to do the long division of polynomial. That will just be x. Then you deal with the rest. So this quotient, the result of this quotient is the oblique asymptote, which we can see from the background here. It's always forming a straight line that is slant, which is why some people call it oblique or slant asymptote.